Imagine you're playing a game of hide and seek with the universe itself. You try to pin down an electron, but the moment you know where it is, it slips away at an unpredictable speed. And if you measure how fast it's moving, suddenly you lose track of where it is. This isn't a limitation of our tools or technology. It's a fundamental law of nature, one that tells us the universe has built-in limits to what we can know. This is Heisenberg's uncertainty principle, one of the most profound and mind-bending ideas in all of physics. To understand why this principle exists, we first need to see how the quantum world differs from the everyday world we're used to. In classical physics, the physics of baseballs, cars, and planets, we can measure both the position and momentum of an object with perfect precision, at least in theory. If I throw a ball, I can calculate exactly where it will land based on its speed and direction. But in the quantum realm, things don't work that way. At the scale of electrons, photons, and other tiny particles, the rules change. These objects don't behave like tiny billiard balls, they behave like waves, or more accurately, like smeared-out clouds of probability. This is the famous wave-particle duality, the idea that quantum objects exhibit both particle-like and wave-like properties. And it's this duality that leads us directly to the uncertainty principle. In 1927, Werner Heisenberg proposed that there's a fundamental limit to how precisely we can know certain pairs of properties of a quantum particle. The most famous pair is position and momentum. The more accurately you measure a particle's position, the less you can know about its momentum, and vice versa. This isn't because our microscopes are too weak or our sensors too slow. It's because the particle itself doesn't have a perfectly defined position and momentum at the same time. The uncertainty principle is often written mathematically as xp2, where x is the uncertainty in position, p is the uncertainty in momentum, and is the reduced Planck constant, a tiny but fundamental number in quantum mechanics. A helpful way to visualize this is to think about waves. A particle with a perfectly defined position would look like an infinitely sharp spike, but to create such a spike, you'd have to combine many different waves of varying wavelengths which correspond to different momenta. The result is that while the position becomes sharp, the momentum becomes completely spread out. On the other hand, a particle with a perfectly defined momentum is like a perfect, infinite wave with a single wavelength, but such a wave is spread out over all space, meaning its position is entirely uncertain. This isn't just a mathematical quirk, it's been confirmed by countless experiments. One of the most famous thought experiments illustrating this is the Heisenberg microscope. Imagine trying to measure the position of an electron by bouncing a photon off it. The photon must have a very short wavelength high energy to resolve the tiny electron, but this means the photon delivers a sharp kick, disturbing the electron's momentum. Conversely, if you use a low-energy photon to avoid disturbing the momentum, its wavelength is too long to give a precise position. No matter how cleverly you design the experiment, you can't escape the trade-off. There are some common misconceptions about the uncertainty principle. One is that it's just a result of our clumsy measurement techniques, that if we had better tools, we could overcome it. But this isn't true. The principle is a fundamental property of quantum systems, not a limitation of technology. Another misconception is that it means quantum mechanics is purely random. While quantum mechanics does involve probabilities, the uncertainty principle is more about limits on knowledge than randomness per se. The implications of this principle are vast. It shapes the behavior of every atom and particle in the universe. For example, it's the reason electrons don't simply spiral into the nucleus of an atom. If they were confined too closely, their momenta would become wildly uncertain, creating a kind of quantum pressure that keeps them in stable orbits. This is why matter doesn't collapse in on itself. The uncertainty principle also plays a crucial role in modern technology. In electron microscopes, the resolution is fundamentally limited by the fact that high-precision position measurements require high-energy electrons, which in turn disturb the system being observed. Quantum computing relies on manipulating particles in ways that embrace their uncertain properties rather than fighting them. Even the precision of atomic clocks is constrained by quantum uncertainty. Beyond technology, the principle has deep philosophical implications. It tells us that the universe is not deterministic in the way classical physics once suggested. There are limits to what we can predict, not because of our ignorance, but because reality itself is fuzzy at the smallest scales. This was so unsettling to Einstein that he famously objected, saying, "God does not play dice with the universe." Yet experiment after experiment has confirmed that, dice or no dice, the uncertainty principle is here to stay. So what does this mean for our understanding of reality? It means the universe is far stranger and more mysterious than it first appears. The more closely we look, the more we find that certainty itself is an illusion, that at the heart of everything there is an irreducible uncertainty, a fundamental limit to what we can know. And perhaps that's the most profound lesson of all. The universe doesn't owe us perfect knowledge. It simply is what it is, and our job is to explore its rules, no matter how counterintuitive they may seem. Heisenberg's uncertainty principle isn't just a footnote in physics, it's a cornerstone of our understanding of reality. It reminds us that the universe is not a clockwork machine, but a dynamic, uncertain, and deeply fascinating place. And who knows? Maybe the next great breakthrough in science will come from embracing that uncertainty rather than resisting it. After all, in the words of another great physicist, Richard Feynman, if you think you understand quantum mechanics, you don't understand quantum mechanics, and maybe that's exactly the point.